Hello, this is video 81. We're going to be describing simple harmonic motion. We just started talking about it in the previous video, so just a little bit more details in this one. So we've already seen that we can use a cosine function, such as this one over here, to describe an object undergoing simple harmonic motion. And this cosine function looks like this following graph, where when the motion begins at time equals 0, then x, the position of the object, is equal to the amplitude. The amplitude is that maximum displacement from the equilibrium position. So you can see the mass starts right here, or right here, which is the amplitude. And then, as time moves on, the object is going to oscillate. It's going to go through the equilibrium position right here. Then it's going to go down over here for that negative amplitude. Then it's going to go back up to the equilibrium position. And then it's going to go back up to the maximum amplitude. So that's what's shown here is a complete cycle. The time for a complete cycle is called a period. So we see that at time is equal to the period, x is equal to the amplitude again. So we've already seen this equation, but now we can look at two new equations, one for velocity and one for acceleration. So over here we have the function that describes the velocity of your object that is undergoing simple harmonic motion. Now this was actually derived by taking the derivative of the previous equation, but that requires calculus, so we skipped that in this class, so you just have to accept this equation. This equation is shown right here. This shows the velocity. So you can see it looks like an upside down sine function where x is equal to the amplitude at the beginning of the motion here. V is equal to 0. So you can just assume that you are either releasing this object here from rest at this point, or it has already gotten back to this point, and then that's the maximum compression, so it has to stop before going back down again. So at the amplitude, v is equal to 0 because the object stops. And then at x equals 0, so this is when the object is going here through that equilibrium position, you can see the corresponding v in this graph. V is negative for this case, and it has reached a maximum value. So all we're saying here is that the object is going down, and so we're calling that motion negative right here, and it has been speeding up due to that spring force, and it speeds up to its maximum value when it's in equilibrium, because after it passes through equilibrium, it slows down until it stops right here when it has reached a negative amplitude. So you can see that when it has reached a negative amplitude, it stops, and then it's going to speed up again until it reaches the equilibrium position again, going in the opposite direction. So now you have a V max here at equilibrium. So it's good to be able to understand these graphs. The only graph that we're going to be analyzing in this class is this position versus time graph. So this graph here is just showing you what this function looks like, and it's helping you see that, okay, when my object is at the maximum amplitude here, this graph doesn't tell me that v is equal to 0, but this one does. So there's also a note here that this maximum velocity that the object has at the equilibrium position is equal to 2 pi f times a. And again, this just comes from when you take the derivative of that position versus time graph, this term here comes to the front. So let's take a look at the acceleration graph. This one comes from taking the derivative of the velocity graph. So in this class, we're just going to accept that it's going to look again like a cosine function, but it's an inverted cosine function. So what is important to know about the acceleration of a mass on a spring? So these are the two important things right here. when x is equal to the amplitude, so at the beginning of the motion again, a, the acceleration, has a maximum value. When it starts over here, the acceleration is negative. Can you think why that is? Well, remember that this spring has just been compressed upward. The displacement from equilibrium was upward. That means that there's a force that is pushing it down. So if the force is downwards, that means that the acceleration is down. So that's why the acceleration is negative. So as the mass goes through its motion, when it reaches its equilibrium position, can you tell what the acceleration is without looking at the acceleration graph? Well, at the equilibrium position, that means that x is equal to 0. That means if you look at that spring force, F is equal to negative kx. Well, if x is 0, that means the force is 0. If the force is 0, that means the acceleration is 0. So the only reason that I'm showing you this graph is because it's showing you that. You can see over here, when x is equal to 0, corresponding to this position, look at the acceleration, it's 0 as well. When x is its amplitude again in the negative direction, you can see that now the object has its maximum acceleration. And that's because there's a force that's pulling the object back up, so there's a positive acceleration. It's a maximum acceleration, well, first of all, because it has to change the direction of the mass, but also because at this position, the mass is at the maximum amplitude, the maximum distance from equilibrium. That means that the value that you put in for x is the biggest possible value. That means you have the greatest possible force, which means you have the greatest possible acceleration.